Hello friends. Now today we discuss the formula for radial acceleration. So first we radial acceleration. Now we find the formula for radial acceleration. Let us suppose that there is a moving particle which moves on a plane curve Let us suppose that there is a moving particle which moves on a plane curve at time t. The moving particle as at point P, and after and at time t plus del t, the particle is at Q point. Let us suppose that a particle moving on a plane curve at time t, the particle is at P point, and at time t plus del t, the particle is at Q point. Let us suppose that the polar coordinate of PB are theta, and O be the pole and OX be the initial line. So OP is the radius vector, which is equal to small r, and angle XOP, this is equal to theta angle, this is vectorial angle. Now we join O and Q point. So let us suppose that the polar coordinates of QB r plus del r and theta plus del theta. So the radius vector OQ is r plus del r, and angle XOQ, this is equal to, and angle XOQ, this is equal to theta plus del theta. Let us suppose that there is a particle which is moving on the plane curve, and at time t the particle is at point P, and at time t plus del t the particle is at point Q. There is O is the pole, OX is the initial line, join OP and OQ. Let us suppose that the polar coordinate of PB are theta and QB r plus del r and theta plus del theta. So the radius vector OP is equal to small r, and angle XOP, this is equal to theta here, and radius vector OQ is r plus del r, and vectorial angle XOQ, this is theta plus del theta. Now this angle is theta here, and this angle is theta del theta. This angle is here del theta. So whole this angle is here theta plus del theta. Now we find the angle POQ. This is equal to angle POQ. This is equal to angle POQ. This is equal to angle XOQ minus angle XOP. Here angle XOQ, this is theta plus del theta, and angle XOP, this is theta, so theta is cancelled out, so angle POQ is equal to del theta. Now we know that the velocity component along the radius vector, this is radial velocity denoted by u. Here u is the velocity component along the radius vector OP, this is the radial velocity, and the velocity component perpendicular to the radius vector at P point is called transverse velocity, which is denoted by V here. So here small u, this is the radial velocity along the radius vector OP, and this is called radial velocity. Velocity component perpendicular to the radius vector OP at P point, this is denoted by V, is called transverse velocity at P point. Now we take velocity along the radius vector OQ is u plus del u. Here u plus del u is the velocity along the radius vector OQ. And we know that the velocity along the radius vector is called radial velocity. So radial velocity at point Q along the radius vector OQ is u plus del u. Now we draw here a velocity perpendicular to the radius vector OQ at Q point is v plus del v. V plus del v is the transverse velocity at Q point because it is perpendicular to the radius vector. You can see here u plus del u, this is the velocity along the radius vector OQ, so this is the radial velocity at Q point. And the velocity v plus del v, which is perpendicular to the radius vector OQ at Q point, so this is transverse velocity. Now we draw a line which is passing through Q point, and parallel to OP. Here suppose that this is M and this is N point. Now you can see here this is MQN, which is parallel to the radius vector OP. Here MQN is parallel to the radius vector OP. Since we know that this angle is del theta, so this angle is also del theta, because these are the corresponding angles. This and this angle is the corresponding angle. Now we find the component of velocity along Qn. Now we find the velocity component of u plus del u in the direction of Qn. So this component is u plus del u cos del theta. This is the horizontal component along Qn. Here we find the velocity component of u plus del u along Qn. Because this angle is del theta, so velocity component of u plus del u along Qn is u plus del u cos del theta. Now we find the component of u plus del u. We draw a line which is perpendicular to Qn. So this is Qn, perpendicular to Qn. Now we find the component of u plus del u along this perpendicular line. So this component is u plus del u sine del theta. Here we find the component of the velocity u plus del u perpendicular to the MQN. Here we find the component of velocity u plus del u in the direction perpendicular to MQN, that is u plus del u sine del theta. This is the vertical component. Now we can see here this angle is 90 here. So this angle is 90 here. This angle is del theta. So this angle is 90 minus del theta. So also we can see here this angle is 90 degree, because this and this is perpendicular. So when we subtract 90 minus del theta from 90, we get this angle is del theta. Now we find component of v plus del v plus del v along this direction. So this is v plus del v and cos del theta. This is the horizontal component of v plus del v in perpendicular direction of m, q, n. Here component of the velocity v plus del v in perpendicular direction of m, q, n is v plus del v cos del theta. This is the horizontal component. Now we find the component of v plus del v along qm. This is v plus del v and sine del theta. This is the vertical component. Here this is vertical component and this component is horizontal. V plus del v along the perpendicular direction of mqn is v plus del v cos del theta, and the component of v plus del v in this direction qm is v plus del v sin del theta. Now this v plus del v sin del theta in opposite direction qn can be written as minus times v plus del v sin del theta, because the direction is opposite here. You can see here v plus del v sin del theta in the direction of qm and minus times v plus del v sin del theta, this is the direction in the direction of qm. Now we find the radial acceleration. So we know that here radial acceleration, this is equal to limit del t tends to 0, change in velocity in time del t divided by del t. We know change in velocity along the radius vector, in time del t divided by del t. We know that the radial acceleration is equal to limit del t tends to 0, change in velocity around the radius vector in time del t divided by del t. Here we can see change in velocity, that means final velocity minus initial velocity. Final velocity along the radius vector at q point, this is equal to u plus del u cos del theta minus v plus del v sin del theta, and this is the final velocity at q point along the radius vector. U plus del u cos del theta minus v plus del v sin del theta, this is the final velocity at q point along the radius vector, minus initial velocity at q point along the radius vector, at p point along the radius vector. Here the radial velocity at p point along the radius vector is u here, divided by del t. Now we expand here cos del theta and sin del theta. So this can be written as u plus del u and 1 minus del theta square by factorial 2 plus del theta whole power 4 by factorial 4 minus and so on, minus v plus del v and expansion of sin del theta is del theta minus del theta whole cube by factorial 3 plus and so on, minus u divided by del t. Now we know that here del theta is very small quantity, so neglecting all the powers of del theta, neglecting all the powers of del theta here. So here we can write del theta is very small, so neglecting all the powers of del theta, so we get limit del t tends to 0, u plus del u and multiplied by 1 minus v plus del v multiplied by del theta minus u, divide by del t. Now we can see here, this can be also written as limit del t tends to 0, u plus del u minus v del theta minus del v del theta minus u divided by del t. Here we can see that del theta is small quantity, del v is also a small quantity. The product of del v and del theta is also a small quantity, so we neglect del v and del theta. Neglect del v into del theta, we get limit del t tends to 0, u plus del u minus v del theta minus u divided by del t. We can see here this u is cancelled by this u, so this is limit del t tends to 0, del u minus v del theta divided by del t. Now this can be written as limit del t tends to 0, del u upon del t minus v del theta upon del t. Now we taking limit, we get here du upon dt minus v d theta upon dt. Now we can see here, this is d theta upon dt. And we know that this is the du upon dt. This can be written as d by dt of u. We know that u is the radial velocity, and radial velocity u is equal to dr upon dt minus v. This is the transverse velocity. So transverse velocity, we know that this is equal to r d theta upon dt. This is value of v into d theta upon dt. We know that u is the radial velocity, and radial velocity u is equal to dr upon dt. And v is the transverse velocity, which is equal to r d theta by dt. So when we differentiate dr by dt with respect to the time, we get d2r by dt2 minus r. Here d theta by dt multiplied by d theta by dt, so it becomes d theta by dt whole square. So we can see here the radial acceleration is equal to d2r by dt2 minus r d theta by dt whole square. This can be also written as r double dot minus r theta dot square. So this is the radial acceleration. Thank you.